Okay, so today's webinar is about a little bit about economics or about benefits that you can get out of hydraulic modeling, and also about the different factors that play a role in modeling. So let's get started. So first, let me acknowledge our partners in different countries. We have our main development partners of Computational Hydraulics Group at the University of Zaragoza in Spain. Also, we have a research and collaboration agreement with NOAA, North Central River Forecast Center. Our main user interface is SMS, and we have also a partnership or an agreement actually with Aquaveo. And also we have an ongoing collaboration agreement with Autodesk, where we are developing a InfraWorks flood plugin using RiverFlow2D. And you may want to take a look at that. It's free. If you go to the Autodesk Labs, you will be able to download both InfraWorks 360 and RiverFlow2D flooding model plugin, and is available in beta format free until June this year. Eventually, this will become a full product in the Autodesk set of products. Okay, so let me tell you a little bit about the motivation of this particular webinar. And what actually motivated me to prepare this webinar was a recent post on the LinkedIn Hydraulic and Hydrologic Modeling Forum. And there was a particular post that said something like this. With zero cost two-dimensional models and all other things being equal, why would one choose to spend thousands of dollars on commercial products rather than using, for example, HEC-RAS 5? So I thought that was a very appropriate post, valid post, and I would like to comment on this throughout the webinar. So in a sense, the main purpose of today's webinar is to discuss about this question and try to give you some light or some insight in the different aspects that are involved in this particular question. So in other words, the question is, why would I use or pay for using a two-dimensional model if I have other models that are free or have zero cost? So that's in other words that question. Now, the purpose of today's webinar is first I want to give a brief introduction to some terms that are, I think, in my opinion, misused in many cases. For example, public domain software, proprietary software, open source, and so forth. So I will discuss about this. I will discuss about factors affecting the total cost of modeling, and I want to stress total cost here. And a question we would like to answer is if a commercial model can be more cost effective than other models that are not paid. I will also show you a brief 7 minutes demonstration video on how to set up and run the RiverFlow2D model, because I think it will give you an idea, for those of you not familiar with the model, how fast and efficiently you can set up and run a model such as ours. And of course, I will be happy to answer any questions you may have. I will not be able to answer them, probably all of them, through the webinar. But I will stop at the end and answer the questions that time allows. So first, I want to discuss what is actually public domain software. And the reason that I want to discuss this is also because there are many instances that I've seen where the term is used in the wrong way. So the public domain software is defined or is accepted to be a software that has absolutely no ownership. There is no copyright, there is no trademark, there is no patent on that type of public domain software. There are no restrictions to use the software in any way you want. And also the software can be modified, distributed, or even sold without any attribution to the ownership or the developer of that software. That is what is universally accepted as a public domain software. And there is also the concept of proprietary software. And this proprietary software is usually accepted to be a non-free software. And when I say non-free, it's not in terms of paid or zero cost, but free in the sense that you have freedom to use the software in any way. So in the case of proprietary software, you have restrictions on the use of the software. This software is not necessarily commercial, so the term proprietary is not related necessarily to paid or non-paid software. It's not also open source, so the source is closed, is maintained. So, for example, all Apple software is proprietary, as there are many other softwares that is proprietary that the open source is not available. So there is no, you cannot use the source freely. And in general, the proprietary software places restrictions on use, modification, distribution, on how you use the software in general. Now, the open source software is a software where the actual program code is made available with the license. So you can make use of the software, but also you can modify the software if you know how to do it, because you will have available the code to do that. In that case, the copyright holder provides the right to change or do whatever you want, or certain restrictions may apply on how you modify the software. And also, you can, in many cases, this is software that can be developed as a collaborative public manner. So you have many people contributing to change the code. And also, it's not necessarily zero cost. So you can have an open source model that you need to pay for it. Now, let me give you a couple of examples here. First, on proprietary models, commercial models, two-dimensional hydraulic models in this case, RiverFlow2D is our own Hydronia model. Mike 21, the DHI model is a well-known model. There are many others, but these are only two of them. And this proprietary commercial models are paid, so you need to pay to get a license to it. And the license cost covers the development, the maintenance, and the technical support, and other aspects of the continuous development that usually this this software has in time. Now there is another example of in this case is a not zero cost software is HEC-RAS. Like many people say you see online and in many venues, you see that saying that HEC-RAS is public domain. HEC-RAS is not public domain. It's proprietary closed source software. You don't get access to to the model code. The reason that is so is that the U.S. Army Corps of Engineers that developed this software discourages the distribution of the source code, and they say that the actual software will remain property of the HEC Center that is part of the Corps of Engineers. So it's a zero cost software or free software that you can use it without paying anything, or almost, but it's proprietary. It's closed software also. Now, I want to also mention that in this particular case of the HEC-RAS model, it has zero cost for people outside the United States, because actually in the United States, as taxpayers, all taxpayers contribute to funding HEC-RAS development, so it's not totally zero cost for people living in the United States. And also the technical support is limited in general to the scope of the U.S. Army Corps of Engineers. So these are two examples of zero cost and non or commercial models. Now let me go back to the post that motivated the webinar. Now the key words here that I want to focus on is that what it says here, is free or paid. Here you want to pay, or it makes sense to pay for a model, or you want to use a zero cost model. Now the main focus here is that the post says all other things being equal. So with zero cost two-dimensional models and all other things being equal, well, what are these all other things that are equal to make this a valid question? Well, the things that these things that I will discuss now are not as equal as they may appear. So there are many factors that play a role that are different in the models, that they may appear to be the same or equivalent, but they are not always the same. So models are different. Different models offer different options and so forth. And the end result may sometimes be the same or equivalent, but they're not always equal. The models have different capabilities, different speed, they run faster or slower. They may be easier or more difficult to use. Some models are updated and fixed very quickly. Some other models are not. They may include technical support or not. So there are many differences between the different options you may have to model two-dimensional hydraulics. Now, the main factors that affect cost modeling tasks are many, but one of them obviously is the software price. That is, what originated the question. But also, when modeling, you need to have a computer and hardware to do your modeling. And additional software, you may need to have GIS software, word processing software, and so forth. And the computer may need to have some limitations on the memory, the processors you use, and so forth. Then you need specific tasks to make. GIS pre-processing of the data. You need to process the data to put it in the format that is more appropriate. You need to conceptualize your hydraulic situation. How are you going to conceptualize the site, the inflow, outflow conditions? Where are you starting? Where are you ending the mesh? Are you going to develop the mesh, refine in some areas and less refined in some other areas, and so forth? There are many things that are involved in the model conceptualization. Then the model setup itself, how you set up the model, and this involves the use of usually of a graphical user interface. Then when it comes to running the model itself, you have the issue of numerical stability and consistency. If the model is stable, is not stable, you need to tweak parameters here and there, so forth. Then when you have the model stabilized and so forth, you need to run the model and how fast the model will perform in your particular project. It takes minutes, it takes hours, it takes days. That play a big role in the cost of modeling tasks. Then when you have the results, you need to analyze the results and look at the what they mean, make some evaluation and so forth, and then obviously you need to post-process, generate plotting maps, animations, and things like that for presentations. So let's go one by one of these factors. So for example, the model cost. Usually model costs involve the actual price of the model license. And we believe that there is a balance between the cost and value that you get out of the model. It's not necessarily that the more it costs, you get more value. So there is a sweet spot between cost and value that for a reasonable cost, you get the best value out of the software. That's our point. But typically, this is a one-time payment. So even though you have maintenance maybe of the model for updates and so forth, but the main cost it occurs one time. That can be distributed throughout many projects. So in general terms, you get diminishing cost as the more you use the model in different projects. It works the same for computer and additional software. So if you use the same computer for 10 projects, you will get less cost as the more you use it. Now, with regards to GIS preprocessing and model conceptualization, it does not always depend on the selected model for the most part. So it's a task that is required in all projects, almost regardless of the model you want to use. The model setup, it highly depends on the graphical user interface. And we are assuming that most modern models have a fairly decent user interface. We use the SMS, but it's essentially a task that is required in our projects. And typically, you tend to use the one that you know best. And so you have some models that use the SMS, and some other use their own user interface. But they mostly work decently for the most part. In regards to numerical stability and consistency, this is highly variable among models. And surprisingly, when you compare different models, you will find highly variable results between the models in regards to the stability and consistency. In some numerical models, the instabilities may require to tweak the model to make it work. So you have many parameters there that are normally numerical constants that you need to move up and down, and they normally require a lot of work, and it's not always consistent. And this is something that if your model is not robust or is not consistent, it will require the same process for most projects, and is a very time-consuming task. So this is where some of the models start to diverge, and they may perform very differently. Well, it may end up creating situations that you want to avoid at all costs. So you get frustrated with the model performance, and that sometimes lead to some actions that are not want to avoid at all costs. Well, the model speed is also very important, and is highly variable among models. And this cartoon here, it says, when the model senses that you are in a hurry, it automatically slows down. So, sometimes you need to perform very quickly. You need the results very quickly, and the model, it just continues and continues, taking time to take to produce results. So what this task involves is monitoring and waiting for runs, and that is a very time-consuming task as well. And it's also, depending on your model, require in all projects, because most projects require, depending on the model, long computer times. In regards to analysis and results and GIS post-processing, it's more or less common to all models. So a summary, from the factors that we enumerated, we have the actual model price and the price of the computer, that is a one-time cost. But then you have a number of time-consuming tasks that are required for all projects. And the percentage that are indicated here are very approximate, and they were gathered after many years of experience doing modeling. I started doing two-dimensional modeling in 1981, 35 years ago, and the tools have evolved quite significantly since then. But the process is more or less the same, even though the tools are much more efficient now. But this percentage are based on our own experience doing modeling for many years. So in graphical form, the different factors here are presented in bars. But what I want to show you is that the actual cost of the software is not actually is the lowest important factor in regards to the total cost, with the total cost of modeling for consultants. And the two tasks that we have found that they take more time is the actual tweaking of the model to make it work, and monitoring for runs. So the model stability and how the model performs, and how you fast or quickly make it work, and the monitoring and waiting for runs, the speed of the model, play the biggest role in affecting the total cost of modeling. So I want to talk to you about the RiverFlow2D model, because obviously it's a hydrology model, and I want to give you a brief overview of what it does, because we are going to make a demonstration of how it works and compare with other models. So RiverFlow2D is a combined hydraulic model based on flexible mesh of triangles that can be adapted to any geometry, and it uses a finite volume numerical engine that can handle supercritical, subcritical regimes without any restriction. It has been extensively validated, and it also does sediment transport, pollutant transport, modern debris flows. It can include hydraulic structures in 2D, like bridges, weirs, and is seamless integrated with SMS GUI. Very importantly, it has a GPU module or a GPU version that take advantage of the graphic processing cards, and I will talk a little bit about this today. So the main numerical properties, what's the bottom line for users about using RiverFlow2D model? First is accurate regardless of the flow regime. It doesn't matter if you are running in high, low velocities, big gradient, convergent, divergent flow, and so forth. Any hydraulic situation is handled accurately. And this is thanks to the use of a very accurate and highly tested finite volume method. The numerical solution is not sensitive to the time step for a given mesh, provided that the current number is less than 1. And this is very important because there are some models that are sensitive and overly sensitive to the time step, and that creates an additional task that is not, what it ends up being is a time-consuming effort that is not necessary usually. So RiverFlow2D models have been tested, and it's, as I said, it's always stable, consistent, and convergent on any real riverine flow situation. Now, the hydraulic components include culverts, internal rating tables, sources and sinks, bridges in 2D, gates in 2D, weirs in 2D, so you can model levees, so sound walls. You can also have levees with variable crest elevations along the levee or the weir. And we recently added the variable roughness with depths to model vegetated terrain. The hydrologic component include a distributed model for rainfall and evaporation and infiltration with 3 different infiltration models. It can be used combined with the hydraulics, and you see here an example of the output that you can get out in a structured hydraulic structure study. This study was actually done by Stantec. The model can do, as I said, dam break flooding because it can handle supercritical and subcritical flows. As I said, you can set up and visualize a model like this very quickly. Now, about the RiverFlow2D GPU, one of the issues that we had many years ago is that non-parallelized models that run sequentially in the code, tend to be very slow, or also poorly parallelized models. And the reason is that the CPU processors are not getting any faster, and they are normally optimized for single threads, so one operation at a time. So the only way you have to accelerate the models is parallelize it, and you need to go to multiple processors. And in the many years ago when I started in the development area, we only had the options of using supercomputers. So if you wanted to run a model with 200 processors, you needed to get some computer time out of these big centers of supercomputers. Now nowadays things have changed quite a lot, and we now have the graphic processing units, for example, NVIDIA, which are the cards that we support. And the NVIDIA cards are designed to accelerate graphic rendering, or were designed to accelerate graphic rendering initially, but they can now be used for accelerating the models, of course, provided that the model has been programmed for that purpose. So this is some of the most common used cards that we have tested. And as you can see here, some cards have thousands to almost 3,000 processors or cores. So these cards become very efficient when used in conjunction with the RiverFlow2D model to handle simulations and very quickly. I will want to show you one example. This is a test that was done by Aquaveo in an actual project that was related to a numerical analysis of a whitewater kayaking training site. And there was some physical model done And so this was a project where several models were applied to test them in this application. So there was a mesh that was medium size for nowadays standard 600,000 triangular elements with a more or less typical computer. And we also ran the model with GPU NVIDIA Titan Black card, the RiverFlow2D GPU model. Now, Aquaveo ran the SRH2D model, two-flow, finite volume, and RiverFlow2D in the CPU and GPU versions. But what I want to point out here is that the run takes about, a long time, 20, 30 hours in CPU versions without parallelization or with medium parallelization. And the GPU version takes a tenth of the time of the fastest model of this table here. So this has a very significant impact on computer times, the GPU version. Now, is that worth it? Well, it requires software and hardware investment. Of course, you need to buy a model and you need to buy the appropriate hardware. But just a simple check here. If you assume a typical project that requires 50 runs, which is not uncommon, based on the practice you need to make and different scenarios and so forth. And if you're saving 12 hours, only 12 hours per run, you are saving 25 days in a single project. So it's totally efficient to, and we think worth it for practical applications. Now, in regards to consistency and so forth, we have run a number of tests, and this is just one of them, this UK benchmark. This is not an idealized test. It's actually a real site where a dam break analysis is made. And the idea is to test different models in this high slope area with actual topography and a hydrograph here upstream that travels downstream as it moves through this valley. So the idea is to check models at different locations that you see marked here with these numbers, 1 to 7. So these are locations where the UK benchmarks requires the models to be tested on. So when we did this model initially, we found very peculiar results for some models. This is the RiverFlow2D, the one in orange here. These are velocities and water elevations at different locations. But what we found interesting is that some models we're very far from others. For example, HEC-RAS 2D beta version with respect to RiverFlow2D or SRH2D, both in water elevations and also in velocities. And we then found that some models are very sensitive to time step in some situations. And that's the case of HEC-RAS 2D beta, the latest one. You can see here how it varies with time step. Now, the velocities change quite significantly, and also the depth can have significant errors in some points. Now, the HEC, now let me, before telling you what the HEC Center said about this, but we ran the time sensitivity test with RiverFlow2D, and we found that these results are insensitive almost completely to the time step or the current number that you use in the range that we recommended. Now, runtimes are very, very significantly RiverFlow2D. Even the CPU without parallelization is much faster than any of the other models that we tested. You see here the results of HEC-RAS 2D and also SRH2D. And the issues that we found is that velocities and depth for this test are very sensitive to time step. And also that the solution deteriorates when you reduce the time step. So it looks to be a lack of convergence. It actually improves when you increase time step, and the difference in velocities and depth changing time step are very high at some locations. Now, we consulted this with the Corps of Engineers, and they are working in a solution for that is not made available yet. But what they indicated is that the solution should converge when you reduce the time step and the mesh simultaneously. Now, we couldn't do that for that particular test because the actual UK test require a specific mesh. So, and most models do not show. The models that have been tested against the test 7, like 2Flow or Mike, do not show this sensitivity to the time step either, in the same way that RiverFlow2D does not. So the bottom line here is that in some situation, according to the Corps of Engineers, where you have convergence and divergence flows and very rapid changes of velocity, you may get a significant time step variability of the model results. Now, in the case of RiverFlow2D, the volume conservation, as in all simulations, is virtually zero. It's unsensitive to time step, and in general, it's much faster than both HEC-RAS and SRH2D, and many times faster in general. Now, let me give you, to complete this part, a demonstration on the use of the RiverFlow2D model. It's an actual computation, but it's a video that is included in most of our distributions. It's called RiverFlow2D Setup in 8 minutes. It actually takes less than 8 minutes, but it gives you an overview from zero, starting from zero, how to set up a model and visualize results using RiverFlow2D within the SMS system. So let me start the video, and I will. Okay, so the first thing we do, we open the SMS program, and we locate the RiverFlow2D template, which is the one that creates the whole RiverFlow2D system within the SMS program. So we go ahead and open that. This area property is the conceptual coverage where we are going to enter the domain extent. We'll define that as a type model generic 2D mesh. And then we import the elevation data set. This file here is an XYZ data. We use the import wizard. It's a space separated file. And here's the points that represent the elevation of the area that we are going to model. This is the main river. We can plot this using contour schemes, and you can see the reds, which are the lower elevations, and the greenish, which are the highest elevation. So the flow will come from upstream to downstream in this direction. Okay, so we'll set the projection for that, which is useful for later use for exporting to Google Earth, mapping, and that type of plotting. We use a state plane. Coordinates for Washington North, which is the one that covers this area. And the information is in feet. Now, the next thing we do is to import, if you have an aerial image, and this is useful for representing your results over that image, and also to enter further data if you want to have them enter here. Now, next step would be to create the polygon that represents the boundary of the model domain you want to enter. So I'll go ahead and enter an upstream line here. This will be our entrance point. We'll have another polyline representing part here, downstream, and then we close the polygon here. So we have, let me turn off the image here so you can see better. Now we have this polygon that creates the extent of the modeling area. Now I'm going to redistribute the vertices by selecting all the arcs that I created, and I will redistribute the vertices to create elements that will be 50 feet in size. So this will drive the mesh generation engine to create elements that are more or less uniform. You can also refine them if you want in different methods. Now, we need to enter the boundary conditions. So the boundary conditions here, I'd enter by selecting the arc and clicking on attributes. And the boundary condition will use here as a discharge. And I will use here as 20,000 CFS upstream. And downstream, I'll use a uniform flow discharge, which is enter here as uniform flow discharge. Uniform flow outflow, I will enter as energy slope 0.025 here. And that completes the creation of the conceptual model. So we have our boundary conditions here, or extent of the model, and we only need to build the polygons, because we need to make sure this is a polygon, and we need to link this polygon to the scatter set that represents the bed elevations. So we click on the polygon and click on attributes. The bathymetry type will be scatter set, taken from the bed elevation scatter set we enter. And that's essentially all we need to complete the model. So now we can go ahead and rename this. Let's rename it as mesh 1. And then we can, and this is optional obviously, but we can now use the feature objects map to 2D mesh to generate the mesh. Now this is the mesh. We can make sure that the mesh is capturing the elevations by using the display options and drawing contours, and we use color fill. So we see here that the actual colors on the elements represent the bed elevations here in the main river. So we have the flow coming from upstream and downstream. Okay, so let's save this as the name of the river, whole river. And let's go ahead and run the model. I will just accept the defaults here, but there are many things you can use to. This is the data input program. I just using the simulation time of 2 hours, output interval, crew number, CFL condition 1. The initial conditions are dry bed, and these are in English units. So let's run the model. So when the model runs, it shows you an image of the water depth or other options that you have here. You may have here the volume conservation error, which is nearly close to 0 most of the time, the time step, and a number of other information that you get in this window. So when you close the model, it writes other results, and also you can import the results back here for post-processing. So if you import the results of the round you just created, you can use this file here, and you can see, for example, the bed, the depth. You can turn off the elements if they become annoying for your view, or you have a number of things you can make here. For example, removing the elements. You can turn off the scatter set. And also, you can view this in 3D if you want it, just for example, let me leave the elevations here. If you use this option, you can visualize the results and zoom in to look at the at your results in the, different three-dimensional views. You have other options to plot fruit numbers, water surface elevation, velocities, and other the results that you get with the model, and you can generate animations as well. I just wanted to give you a quick overview. As you can see, in just a few minutes, you can have a full-blown simulation with RiverFlow2D and SMS. Well, okay. I hope you got the idea of how quickly and rapidly you can generate a RiverFlow2D simulation. And the reason you can do that is not only because the SMS link with the RiverFlow2D is very efficient and you have a lot of features in SMS, but also because the actual RiverFlow2D engine is a very robust, accurate, and fast model. And that's something that you always get in all of situations that you want to model. So I think that the bottom line here is try to minimize time-consuming modeling tasks. And the issue is that some models that are overly sensitive to time step may require necessary amount of tweaking. And we believe that the engineers should better spend their hours or the time analyzing results or performing more scenarios rather than tweaking the model just to make it stable or to make it work. So that's a critical step that you need to take into account. And also, with the RiverFlow2D GPU, you can significantly reduce the modeling cost. Now, the other thing is the technical support. It's not a minor thing. And the issue is that when you have a problem with the model and you don't understand something, who do you call? If you don't have a technical support help desk that you can email, send your project, get the project reviewed, and get it back in a reasonable time, you are sometimes in trouble in doing actual consulting work in 2 dimensions. So again, we believe in these results that the actual areas that require more attention is tweaking the model to make it work and monitoring the model so that they are the most time-consuming task. So again, to close with the initial post that motivated this webinar, with zero cost 2D models and other things being equal, why would one choose to spend thousands of dollars on commercial products rather than RAS2D or other free model? Where we wanted to rephrase that. I think the question is, it should be posed in a different way. So we would put it this way: with very stable, fast, easy to set up, well-supported 2D models, and all other things being equal, why would one choose not to invest on a commercial product that will ensure a much more cost-effective modeling? So that's the question we believe that is better posed. So all things considered, the stable, fast, easy to set up, well-supported 2D model can be certainly more cost-effective than zero-cost models. Well, that's essentially all we had to say today. I would like to take some time to answer a couple of questions we may have. We have a question here on how efficient is technical support. Well, our technical support, we have a pretty well-qualified team of people that have a lot of expertise in technical support of two-dimensional modeling, not only of hydraulics, but also sediment transport, pollutant transport, and so forth. And our response time is usually measured in minutes or hours. Very seldom we take more than a few hours to respond. It depends on the type of question we get, but usually what we do when the question is very involved, or it sometimes relates to complex projects, is that we request to the user to send us the file. We run the model they have developed, and we make a thorough analysis of what the issues of the models are, and we provide a solution. So that's the type of support that we provide for our users. Okay, I have a question here that is related to the comparison of RiverFlow2D with HEC-RAS. And the question is that the HEC-RAS has these subgrid cells that allow the model to run much faster because it resolves the internal bathymetry of the cells. And if we would use that, the HEC-RAS would run much faster. Okay, well, yes, that's correct. However, you have to. I think I have a. Let me see if I have. Yeah, I have a. This one here. I'm sorry. Yeah, I have a slide that shows this because we get this question quite often on our support side. Now, these are the cells in HEC-RAS or in schematics of what the cells look like. So if you use a cell like this, the cells can handle or represent the bathymetry or the topography inside the cell. Now, there is a big difference in what you do here in HEC-RAS or what you could do if you refine the mesh and actually resolve the full equations inside these areas. So what we say is that they are not equivalent in general. So using these cells may give you the impression or the perception that using the cells you get the whole package, but with larger cells and then with less effort. Now, the thing is that these cells internally ignore the momentum transfer. So they do not represent how the velocities are, only continuity is ensured inside the cells. So you're not getting exactly the same results or the same equations in the internal of the cells. So you don't get the velocity details inside the cells. And when you're trying to model rapid flows, you're not actually capturing how the velocity or the flow is behaving here for rapid flows. And the only way to go is to refine the mesh and resolve the full equations. Now, in some situations, very slow flooding situations, that may work, and it may be actually convenient, but you have to use it with care, because if you're running a project with rapid flows, that they may not be, you're not solving the same equations there. So you have to use it with care. I have a question here in regards to how RiverFlow2D compares with the 2Flow. Well, there are two main 2Flow models: 2Flow, the basic 2Flow or classic 2Flow, and 2Flow finite volume. RiverFlow2D is normally more similar to 2Flow finite volume. As far as I know, there is no GPU version of the GPU finite volume. Aquaveo ran a case where they compare, the accuracy is very similar, but the performance is, as you can see here, to flow takes about 32 hours to run this, the finite volume version, or the flexible mesh version, I should say. It takes about 32 hours, and the GPU version, it takes 2 hours in RiverFlow2D. Accuracy-wise, it's similar. I think 2Flow doesn't have two-dimensional hydraulic structures inside the mesh. RiverFlow2D does have it. And also, price-wise, RiverFlow2D is less costly than the 2Flow model. Okay, so we have a few minutes more. Is your software able to set variable that time step to improve stability of the model? Actually, in RiverFlow2D, you don't need to improve stability. The model will always be stable. I haven't found a single case where the model becomes unstable in RiverFlow2D model. And I can tell you I've seen quite a lot of simulations coming from many users worldwide. So the model, what it does is automatically adjust the time step to ensure stability and consistency and convergence always. So it's a matter of the model. You don't need to pay attention to that, and that's one of the reasons that the model is so efficient in doing actual project work. Okay, another question here is it possible to work with different meshes of the same computational domain? Yes, you can refine the mesh. You can set different resolution in different areas. There are many tools to do that, where you can have, for example, you define a polygon and you want smaller elements in that area, and that's obviously possible. Yes, and it's very common. Obviously, I used just in the example a very simple uniform mesh, but in general, that's what you do. Can it model dam break situations? Yes. Well, those of you interested, if you go to our website or if you drop me an email, I can send you a link to view a webinar we gave last year on how to implement a dam break analysis in RiverFlow2D. It's actually one of the main areas of application of the model, because the model handles this very steep valleys that are usually downstream from the dam site very, very accurately. So yeah, that's one of the main application areas, dam breaks. And what hydraulic structures can it model? Well, there is another webinar that deals with hydraulic structures, so I can give you the links for those of you interested. For example, bridges. You can handle bridges in 2D inside the mesh, and the bridges can have situations of pressure flow, overtopping. Those situations are accounted for in the tool. You have also gates, so you can define the gate with the sluice gate operation. You have weirs, culverts, and the culverts are used as one-dimensional connections between two different elements. And the model calculates the discharge based on the Federal Highway Administration formulations. Well, I have more questions, but unfortunately, I'm running out of time. Any questions, additional questions you have posed, I will answer them by email. And you can free to email me and ask me any other question you may have. And again, the webinar has been recorded, and you will be able to watch the webinar or distribute it freely at no cost, zero cost to any of your colleagues if you wish so. Well, thank you very much for attending the webinar, and we'll have next one in a few weeks from today. So thank you very much.